Higher aim. We're going to discuss section 5.2, and in knowing these things and working our way through section 5.2, it's helpful to have these sums. Now, I left this one blank because I wanted to point out something that may help you remember it. So, the sum of the first n integers is n times n plus 1 over 2, but the sum of the first n cubed integers, so like 1 cubed, 2 cubed, 3 cubed, etc., is actually related to this formula. So if you can remember this one, you get this one almost for free because it's the square of this one. So if I square 2, I'll get a 4, and I'll have n squared and n plus 1 squared. So it's exactly the square of this one here. So that's maybe something that'll help you remember this. But we're going to work with finding the area between a curve and the x-axis. And when we do that, we're going to be integrating. So let me define something for us here. And you can see a familiar symbol here. The integral from a to b of f of x dx is defined as this limit, as the limit of the sum from I equals 1 to n of f of x sub I times delta x. Wow, there's a lot of stuff going on here. Let me explain a lot of what this stuff means. So, we're going to find the area between a curve and the x-axis between these 2 points, say between A and B. And let's take a look at a couple things in the actual book here. So here's a good example of this. So here's your A to B. We're trying to find the area between the curve and the x-axis. And we're going to start out by estimating it. We're going to estimate it with these rectangles. So the rectangles have a width of delta x. And the height, you can measure the height in any place in this interval. A lot of times we'll take the left-hand endpoint, the right-hand endpoint, or the midpoint. But you measure the height in any ways, and that's going to be your f of x, or f of x sub I. The area of this one rectangle is going to be the width times the height. And that's exactly what we have here in this sum, is the width of your rectangle. So there's your width times the height. And that's just going to be the area of one rectangle. You've got to add that area up for all the rectangles, and then that gives you an estimate of the actual area between the curve and the x-axis. Here, the width of these rectangles is just the width of your interval divided by the number of rectangles. So, oops, I want to use the other button here. Let me give you an illustration of what's going on here. So you can see that we're trying to estimate the area between this curve and the x-axis. And right now, we're using, a fair number of triangles. I think we got 13 or so triangles, maybe 10 triangles or rectangles. And we get a decent estimate, but, not a great estimate. So what we're going to do is we're going to increase the number of rectangles, and that should give me a better estimate. So let's do that. Let's increase the number of rectangles. Does that look like a better estimate of the area between the curve and the x-axis? Yes. All right. The crowd says yes. Good. And let me, And let's go to extremes. So this is 50 rectangles. What if I did 100 or 200, all the way up to 500? And eventually, what's happening? Eventually, those rectangles get really, really narrow, and the area that they represent cumulatively gets closer and closer to the true area between the curve and the x-axis. And that's what we want to happen. So let's see it again. So you start out with, very few rectangles, and you start increasing. And as you increase more and more rectangles, that's a better and better approximation to the area underneath the curve. So nice. That's what we're doing. You're taking the limit as n approaches infinity. As the number of those rectangles gets bigger and bigger and bigger, that eventually gets to the area. And we're going to define that area as this, f of x, or the integral from f of x from a to b of f of x dx. That's our area. And that's what we're going to be working on finding. Now, there's one other thing that I want to point out here. All semester long, in fact, for many semesters, if you've had me in my class, I've been playing this perpetual joke on you guys. I've been writing section 5.2 with our little integral symbol. And the funny thing is, that integral symbol, even though it's what we use, was not invented by Newton, who invented calculus. It was invented by his rival Leibniz. And it's Leibniz's symbol and his notation that we use much more than Newton's, which was much more cumbersome and tedious. So, okay, so let's practice a couple problems just to get used to this notation and get into the flow a little bit. We'll start with problem number 18. So problem number 18 looks like this. It's the limit recording. Yep, all right, still got sound. So it's going to be the limit as n approaches infinity of the sum from I equals 1 to n of x sub I times the square root of 1 plus x sub I cubed times delta x. What we want to do is we want to translate that into this integral notation. So, okay, let's see if we can't do that. So the first thing is that this is going to be an integral. I think they also tell you, they have to tell you something else here. Yeah, they tell you this is from 2 to 5. And those are going to be the limits of our integration. So this is going to be the definite integral from 2 to 5. Well, the delta x eventually is going to become my dx term here. But what's the function? Well, you got to think of x sub I as really representing our x. So this function is really x times the square root of 1 plus x cubed. And that's it. You're just trying to understand that this notation can be represented using the integral symbol. Nice. Let's try one more like that, just to kind of get in the flow. I want you to do this one ahead of me this time. So for problem number 20, we've got the limit as n approaches infinity of the sum from I equals 1 to n of x sub I star over x sub I star squared plus 4. And this is on, or it's going to be delta x. This is on the interval, is it 1 to 3? Yeah, 1 to 3. So try and write that with an integral symbol. Takers on that one? All right. Integral? Good.
I know it's x
Over,
x squared plus 4.
and then, yeah, and that's it. That's exactly right. Cool. Thank you. What's that? The star is a way to choose points in these intervals. So it could be the left-hand endpoint, could be the right-hand endpoint, could be the midpoint, could be something else. It's just a way to choose the point in those intervals. So remember that what you're doing to find this approximation with this finite sum is you're adding up the area of all these little rectangles. So let me go back to that picture I used in the book just a minute ago. Let's see, right here. So remember, you're getting the height of that rectangle someplace. Now here, x sub I was the height of the ith interval, or height in the ith interval at that point. So this would be f of x sub I star, would be the height of that point right there. Now you could use the left-hand endpoint, the right-hand endpoint, or any other point in between. It's kind of up to you. So that's going to depend on how you work this one. But it really doesn't matter, because as you make these increasingly thin, you're not going to have a whole lot of wiggle room. And eventually, in the limit, those rectangles are going to turn into this nice, smooth function. And we'll get the exact area that we're looking for. Let's do one in the opposite direction. Problem number 34. Problem 32 is the one in the opposite direction. So this time we've got the integral from 2 to 10 of x to the 6th dx. And I want to write this as the limit as n approaches infinity of something. See if you can't fill in the rest. I equals 1. But it's going to be over the interval from 2 to 10. So we put that in there. Well, that's a good question. And I guess I would ask you to hang on to the bitter end a little bit and see that. If we look back at the definition that I started out with, you'll kind of see that as well. All right, so what should go here? X sub I to the 6 times delta x. Good. Now, if you want to put xi to the 6 and then put a little star here, that's fine. But in answer to your question, Omar, x sub I, your points in those intervals are going to be your first interval plus, I guess I should have an I here, I times the width of those intervals. So if I'm at the second interval, then 2 times that width plus wherever I started, that's going to put me at some point in that second interval. So, yeah, it's kind of built in here. All right, let's take a look at problem number 34. I like problem number 34 because it's really starting to get at the connection between these integrals and areas. So I'm going to do my best to draw something like this. So let me kind of zoom out a little bit and try and draw something like that. And look at certain integrals. Here we go. Okay, so all right, it's not drawn really wonderfully to scale. That's okay. We'll get out of it what we need. That's a 4, that's a 2, that's a 4, and that's a 1. 6, and 7. So despite what this might look like, it is actually a semicircle of radius 2, centered at 4 and 0. And they ask us several different questions about this. first of all, the integral from 0 to 2 of our function. And they call this function g of x. So y equals g of x is what's graphed here. dx. Please put the dx's by your integrals, please. And I'm not going to try and explain exactly why, but I do want to see that there. So really what they're looking for is this right here. Is this area. Well, we don't need calculus to find that area. How do you find the area of a triangle? So it's going to be 1/2 base times height. 1/2. The base is 2. What's the height? 4. So that answer should be 4. Okay. Let's try the next part. Next part, we're going to be coming down here. So for the next part, there's a little bit of a twist here. For part B, we want the integral of g of x from 2 to 6 dx. Well, what kind of a figure is this? Semicircle. Good. Semicircle with a radius of 2. So it's going to be 1/2 of pi r squared, right? The normal area would be pi r squared. In this case, it's half of that. So 1/2 times pi times 2 squared is going to be 2 pi. But there's a little bit of a twist here. Because this curve lies below the x-axis, we're going to think of this as a signed area. It's going to be negative 2 pi is the area. It's because, like I said, it's below the x-axis. Finally, we got one last little bit that we need to calculate the area for. And that's this part right here, which is another little triangle. Let's see if we can't find that area. What's the area of that little triangle? Come on, make me look good. Yeah. And what's the base? And what's the height? 1 and 1. So the area here is 1. It's going to be a positive 1/2. I said the area is 1. The area is 1/2. The area is going to be a positive 1/2 because it lies above the x-axis. So I wanted that little piece in place before I did part C, which is the integral from 0 to 7 of g of x dx. And really it's going to be the sum of all three of these areas, right? It's going to be 4 plus negative 2 pi plus 1/2. So 4.5 minus 2 pi. That's the area there. But these integrals relate to areas between the curve and the x-axis. How are we looking at problem number 34 there? Question? No? All right. Let's try another one. Problem number 36. The integral from 0 to 9 of 1/3 x minus 2 dx. All right, well, I'm going to have to do a little bit of work on this one. I guess, first of all, it might serve us well if we had a graph of this, right? So how do you want to graph it? Do you want to use calculator, decimals, or should we actually, I don't know, think? Use our brains. I'm noticing that no one says think. All right, I'll give you some slack. You just took a test. That's fine. All right, so let's do it on our calculators then, right? Because mine is a terrible thing to use, so let's use technology. Okay, I'm just teasing you guys. I don't mean to give you too hard of a time. So it's going to be x divided by 3 minus 2. And I want to see that in the range from 0 to 9. They're telling me where I need to see that. So I need a minus there, don't I? Minus 2. Thank you. So let me set up my window from 0 to 9 on the x-axis. So 0 to 9, scale of 1. And then I'm going to let my calculator do the rest of the work. How do I do that? Zoom 0. Wow, you guys must have been paying attention earlier. Cool. So zoom 0, and it gives me a graph like this. Okay, that's cool. Let me try and draw that graph right here. So something like this. And importantly, the graph crosses the x-axis. Where does it cross? Does anyone notice? 6. Good. 6 and 9. This is going to be down here at -2. At 9, we're up here at 1. So great. Basically, to find this integral, I got to find two areas, right? I got to find, we'll call it A1 and A2. There's a little bit of a catch in finding A1, right? Does anyone know what I have to be careful about when I write down my answer for A1? Yeah, it has to be negative because we're below the x-axis. So, again, these are just triangles, so it's not that big of a deal. Let's see. It's going to be negative of 1/2 times the base, which is 6, times the height, which is 2. And then likewise over here, 1/2 of 3 times 1. So I get -6 plus 3/2, or it would be -9/2. That would be the overall answer to this problem. Okay, not bad. Not bad. So we're drawing a nice connection between the areas of these graphs and this integral symbol. What we're not going to get to today is how to calculate this in more challenging cases. So that's going to wait until we get the fundamental theorem of calculus coming up. But we're looking okay with problem 36. All right. The crowd roars its support. That's good. Problem number 40. Zero to 1 of the absolute value of 2x minus 1 dx. Well, this one's a little stickier because we don't graph the absolute value that often. It's like, wow, what is that? So, suggestions. It'd be nice if I knew the graph of this. Calculator again? All right, calculator again. So, probably not a bad one to do by your calculator because a lot of people forget where the absolute value is. So, hit the y equals key, clear out all the junk there. Does anyone remember where the absolute value is on your graphing calculator? You hit the math menu, then to the right by 1, the first option down is your absolute value. Now, on your old 83s, it'll just say ABS. But on the newer ones, it'll actually give you an absolute value. And you're just going to type in 2x minus 1. If you have an 83, then you need to use a right parenthesis at the end of that. Okay, so we'll play the same game as we did before. We're going to set this up between 0 and 1. So hit the window key, 0 to 1, and then zoom 0. That'll give us our graph. Okay. One quick question for you, and I want a quick answer. When I integrate this, am I going to get a positive or negative answer? Positive, because it's all lying above the x-axis. So you know that this thing should be positive. So, cool. All right, well, Let me kind of graph this, see if we can't figure out that area. So here, and then equal and opposite over here. So this point is 1/2. And what's the height here? I think the height's 2, right? No, it's actually 1. You're right. It's 1. It has to be 1. Yeah, 0 and 1. Okay, so the height's 1 there. That's good. Let's find the area. Area of the rectangle. So I need 2 things, area 1 and area 2. You know what? I think they're going to be the same. So let's see, it's going to be 1/2 of the base times the height. So 1/2 of 1/2 times 1. That's area 1 plus area 2 is going to be the same thing. 1/2 of 1/2 times 1. So twice of 1/4 is 1/2. Nice. Let's move up to problem number 52, which is a problem in the book. Let me kind of zoom in here. Says capital F of x is defined as this function, the integral from 2 to x, and they want you to determine which one of these is going to be the largest. F of 0, f of 1, 2, 3, 4, etc. But keep in mind that this function is really the area to the right of this point 2. From 2 all the way up to 5. So the question is, I'm going to give you a moment to think about it, which of these values is going to be the largest? Now talk to your neighbor about it. See if your neighbor agrees. This is kind of a good problem. Makes you think on this one a little bit. Okay. So let's do a little poll here. How many think answer A? How many think answer B? How about C? D? E? Abstained. Don't care. Want to go home. All right. It is indeed answer A. Okay, why is that? Because as you move to the right, you're getting more and more area. But what have I been saying about the area because it's below the x-axis? It's negative. So the more you move to the right, the bigger and bigger of a negative number you're going to get. And so you're getting larger negative numbers and they're just not going to be the largest value. So the actually, you know what? Actually, we should be f of 2. You know, I don't like this one because we haven't really talked about something here. Now I'm looking at this. F of 0 would actually also be negative, but that's a property we haven't discussed yet. F of 0 would be negative, that'd be negative. F of 2. You know, I'm going to go with F of 2 because F of 2 is 0. These A and B, you know what? Technically, those would be negative values as well. So the largest one is F of 2. Yeah, you know, originally I thought this was a cool problem. I'm not thinking that now. All right, there are some properties we're going to learn about the integral in section 5.3 that make this a little bit easier to digest. All right, so let's go to the last couple problems then, and it's actually getting your hands dirty with some of these calculations, and decided to kind of take it a little bit easy on you in terms of these calculations. I'll give you my own examples, but where you'll see stuff like this, let's see, in the homework, in terms of areas, where is it in terms of the homework? Yeah, so you'll face this in the homework in problems like 21 and 23. You'll see it there. Yeah, I'm not going to assign problem 25. All right, so let's go. We're going to work on finding one of these areas exactly. So I'm going to do my own examples, not the ones in the book. So the ones in the book are just a little bit too hard, and I don't really see the point of making these that hard. So the integral from 0 to 3 of x squared plus 5 dx. Now, you can't exactly get the area between this curve and the x-axis between 0 and 3 with methods of geometry. What's the shape of this graph going to look like? A parabola. So our f of x is x squared plus 5. Let's keep that in mind. And now we need to calculate a couple things. We need to calculate, first of all, delta x. So delta x, I need an x in there. Delta x is going to be b minus a over n, which for us is 3 minus 0 over n, or just 3 over n. Okay, so that's the width of our rectangles. How do you find the height of our rectangles? Well, we're going to need to evaluate that at certain points. So for that, I need, first of all, x sub I, which is going to be a plus delta x times I. A in this case was 0. Delta x was 3 over n times I. So in our first rectangle, we're going to take the area, we're going to find the height when n equals 1, or I equals 1. I'll plug this into my function and get the height. So f of x sub I is going to be f of 3i over n, which is going to be 3i over n squared plus 5. What's that end up to be? Well, it's 9i squared over n squared plus 5. And that's the height of our rectangle. So we've got two things to find the height of our rectangles. Because remember, we're going to treat this as the limit. We're going to treat this just like we defined it earlier. It's going to be the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I times delta x. This little piece right here is the area of one rectangle. Okay. Well, I got to put a few things together. I've got my f of x sub I. I've got my delta x. I need to put those things together right here. And I think I'm going to go to another sheet to do that. So I want the limit. This area is going to be the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I, which is 9I squared over n squared plus 5 times delta x, which is 3 over n. We're going to take the limit as n approaches infinity, and we're going to get the exact area underneath that curve. In fact, let me see if I can't tweak something here for us. Let's go up here, and I'll change this to our actual function. X squared plus 5. And we can zoom out a little bit. And I want to find the area there between 0 and, what was it, 3? 3 is the upper limit? Yeah. So basically, this is what I'm looking for. This area right there. It's 15 and 0, 5. All right. So we're looking for this exact area. And what we're going to do is approximate that using more and more rectangles. We're going to start out with a few rectangles and then add a bunch more. And as we increase the number of rectangles as we take the limit, then in the limit we're going to get the exact area. So let's see how that looks by hand. Well, I'll distribute this and I'll turn this into the limit as n approaches infinity of the sum from I equals 1 to n of 27I squared over n cubed plus 5 times 3 is 15, 15 over n. And I'm going to split this up. In fact, now we'll split it up into two summations. Limit as n approaches infinity from the sum, or of the sum from I equals 1 to n of 27I squared over n cubed plus the sum from I equals 1 to n of 15 over n. Now here's where we're going to get a little bit clever. And we're also going to use those theorems that I gave you at the start of this. This summation depends on the variable I. That's all that matters here. This is being summed with respect to I. So everything else is a constant and can factor out. So this is the limit as n approaches infinity of 27 over n cubed times the sum from I equals 1 to n of I squared. Likewise, 15 over n doesn't depend on I. So I'll factor that out. 15 over n times the sum from I equals 1 to n. I've got to leave a placeholder. So that placeholder is 1. I want to take the limit of this whole thing. Well, let's think. We can clean this up now. Both of these, this sum here and this one here, we can replace that with stuff. This one here is stuff that I gave you at the very beginning of this section, and that is the sum of the first n squared integers. That's this formula, n times n plus 1 times 2n plus 1 over 6. So it's going to be the limit as n approaches infinity of 27 over n cubed, n times n plus 1 times 2n plus 1 over 6. Let's think about this next part. What am I adding up from one term to the next? This is a sum from I equals 1 to n. I'm adding 1 plus 1 plus 1 plus 1. How many 1s am I adding? N of them. So if I add up 1 n times, what do I get? I'll get n. It's just 1 plus 1 plus 1 plus 1 n times. If n was 10, this would be 10. So, okay, we're getting close. Hang tough. Limit as n approaches infinity. Let's clean things up a little bit. I'm going to take the 6 out in front. I have this as 27 over 6. And if I multiply this all out, I'll get, let's see, it'd be 2n cubed plus, what, it'd be 3n squared plus n over n cubed plus 15. All right, now we can get someplace. Now we can really get someplace. In fact, we can finish this one up. As n approaches infinity, what happens with that limit? Yeah. Notice that you've got the same exponent for both terms, both highest degree terms in the denominator and the numerator. So that's 2 over 1. So this limit goes to 2. What about here? As n approaches infinity, this is still 15, right? It doesn't change. So what are we left with? We're left with 27 over 6. Christian, what's that reduced to? Good, 9 over 2. And it's 9 over 2 here times 2. And the 2's cancel, so I get 9 plus 15 is 24. Yay. So that's the exact area underneath that curve. Don't worry. I usually put no more than 6 or 8 of these on an exam. We should probably do one more. I know you're like, I just did an exam. It's your nose. You pick it. But I recommend we do at least one more. Okay. No one's leaving, so we're going to do one more. We'll do this one a little bit. All right. Well, that's the good thing is you can go watch. Amari, you can go back and watch the video in slow motion. All right. Do you want to ask specific questions about this one, or you just want to have another example and get it done? Okay, another example and get it done. These are the easy ones. There's harder ones. These are really the easy ones. I kid you not. All right. So the integral from 3 to 7 of 5x minus 9 dx. This one's going to be a little bit more annoying because the lower limit is not 0. So we'll start by figuring out what delta x is. Delta x is going to be b minus a over n. What are b and a in this particular case? 3 and 7. So 7 minus 3 gives me 4 over n. That's the width of my rectangles. Now I need to figure out where I'm going to evaluate the rectangles. That's my x sub I. That's a plus delta x, times I. So it's going to be 3 plus 4 over n times I. Okay. So that one's not too bad. Now, I got to figure out f of x sub I. Now, granted, you could do this one with geometry, because this one's just going to be, area of a trapezoid, really. But that's not my goal here. So I chose an easy example that we could do in another way. I need to figure out what the height of my rectangle is. Here's the width, here's the height. It's the function evaluated at this point. So f of x sub I is going to be 5 times 3 plus 4i over n. And let's see, if I distribute and clean that up a little bit, let's see, that's going to be 15 plus 20i over n minus 9. So overall, 6 plus 20 over 20i over n. Let's form our function, our limit. Limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I times delta x. That's just coming from the definition. This is the height of your rectangle times the width. So the height is this function right here. 6 plus 20i over n times the width, which is 4 over n. And there's still a limit here. Let's distribute this. It's going to be the limit as n approaches infinity of the sum from I equals 1 to n of 24 over n plus 80i over n squared. Limit as n approaches infinity. I'm going to split this up kind of like I did with the last one. Everything that doesn't involve an I can be factored out. So we're going to do this all in one step here. 24 over n, that gets factored out. I'll have 24 over n times the sum from I equals 1 to n of 1. Plus, let's see. Well, I can factor out the 80 over n squared. So 80 over n squared. And if I do that, what's left? Just I. Now it's at this step that I can really make some progress. This, the sum from 1 to n of 1 is just 1 plus 1 plus 1 n times. So that one is just n. So I get 24 over n times n plus 80 over n squared. And here's where you go back to the formulas from the first part of today. N times n plus 1 over 2. When you do these problems right, the problems that I'll assign you, the degree here and the degree here should match, just like they do here. That cancels out. You're just left with 24. Over here, I get some more cancellation, right? This cancels and this cancels, gives me 40. So I got the limit as n approaches infinity of 24 plus 40 times n squared plus n over n squared. Let's look past the 40. What's the limit as n approaches infinity of n squared over n? 1. So that's a 1. So I get 24 plus 40 gives me 64. And that is your area. Yes, please.
So back when you were cleaning things up and you had 80 over n squared, down
80I over n squared, yes. Down here?
yes.
Right here?
So why didn't you distribute that n to get you n squared plus n and you could remove the n squared?
Well, I got rid of it by taking the limit, right? The limit of this is 1. So I didn't worry about, I mean, I could cancel the n's, or one of the n's, right? But then I have n plus 1 over n. It's still going to have the same limit of 1. So I didn't really need to do any cancellation there. I need to give you some homework here. Let me get that to you real quick. Yeah, I know. You almost got out of here, right? 1 through 11, 19, 29, and 37 has a star by it. Don't know what that means. All right. See ya. Courtney, you had a quick question? How did I get rid of the n squared underneath the 80? Oh, I just moved it underneath here, right? The 2 canceled, and then I just wrote the n squared underneath there. Because it's all one product. If you took the limit now, you're still going to get 40, right? Because you'll have 80 n squared over 2n squared, and the degrees match. So if I was to write this as, let's see, 80n squared plus 80n over 2n squared, like that, the limit is still the ratio of the leading coefficients, which is 40. So a lot of flexibility. All right, take care. Cool.